The next really neat thing that we can do with integration is that we can actually calculate volumes of seemingly bizarre regions. And so here in this kind of pictorial example, I've got this curvy region of 3 dimensions, and here these solid lines indicate the edges that are clear to me in this perspective, and these dashed lines indicate that they're edges, but I can't necessarily see them. And so the basic idea is that I'm going to take an infinitesimal slice, so a very small slice of this region. So let's take an infinitesimal slice. So that's basically just a chunk. I'm going to take a chunk like I've cut it with a knife. Let's say this is a very misshapen piece of bread, and I cut it with a knife, and I have to cut it 2 sides, but I want it really thin slice. And so by thin, I mean that the width of the slice is a little differential chunk of length, which I call dx. Now, if the slice is really thin, then roughly the volume of the slice of bread or a slice of the region is the area of the slice or the area of the cross section times the width. Dx. And so this little what I'll call dV, the differential chunk of volume of the slice, is equal to the area of the slice times the differential chunk of width. So the idea is that I'm going to take a Riemann sum of these things, and so I can approximate the volume by a Riemann sum, where I'm summing over area of slice K times the differential width. And then if I take a limit, I get the integral from a to b of what I'll call the area function, which is the area of an infinitesimally thin slice, times dx. So now let's do an example of figuring out the volume of one of these more complicated regions. So the basic idea is that we're going to assume that the slices have some relatively easily computable area. So in this instance, I've assumed that all my slices of my object are triangles, but the height of the triangle is x squared as I move from x is equal to 0 to x is equal to 1. And so I first need to figure out the area of the triangle. And of course the area is 1/2 base times height. I know the height, it's already x squared. So I have 1/2 x squared. And now I just need to figure out the base. Well, since I've specified that this is an equilateral triangle, I know that this is 60 degrees, this is 30 degrees, and this will be a right angle. And so it's twice the length of this. And so using my ratios, I know that this edge will have a ratio square root 3. This edge will have a ratio 1. And this one will be square root, or just 2. And so since this is x squared, then this would have to be x squared over square root 3, which is equal to 3 over, or square root 3 over 3 x squared. And so ultimately I'm going to have, but remember that's only half because I've only looked at this right triangle. So this is 2 times that, so the 1/2 will cancel out, and I end up with a square root 3 to x squared times x squared, which will be x to the 4th power. So now that I have my area, I know that the volume is given by the integral from 0 to 1 of the area of x dx. But now I know what that area function is, that slice area function is. It's going to be integral from 0 to 1 square root 3 over 2 x to the 4th power dx. So I have square root 3 over, this should have been 3. 1/5 x to the 5th power, evaluated from 0 to 1. And of course it's 0, it cancels out, and so I'll get a net contribution of 1/5. And so I have square root 3 over 15 as the total area. Now we've seen a simple example, and there's a common problem that shows up when you take a solid of revolution. So in this instance, the formula that we had takes on a specific form because we know exactly the geometry of the cross sections, and the cross sections will be infinitesimally small disks. So the idea with the solid of revolution is that we begin with the graph of a function, and then we're going to rotate it around the x-axis. So we're going to spin it all around. And then we see what region of space that carves out. And so here I've rotated this shaded area, and I've obtained this, somewhat urn shape, but it's a filled-in urn shape. And the main thing to note is that the cross section, that is when I take an infinitesimal slice, I'll have a disk. So it'll have width. So it'll be a disk. It'll have infinitesimal width dx. And what's the radius? Well, the radius was exactly determined by the graph of our function f of x. And so what's the area? Well, the area of the slice in this case is the area of the circle. So that's going to be exactly pi times the radius squared, but the radius in this instance is simply the function. And so now we integrate to obtain the volume. So the volume of the solid of revolution is going to be equal to the integral from a to b, which define the limits, pi f of x squared dx. In this example, we look at the function f of x is equal to x squared, and we're going to take the graph and we're going to revolve it around the x-axis to obtain this figure. It's kind of like a cone or a horn that's kind of filled in. So using our formula, we have that the volume of this solid of revolution is going to be the integral from 0 to 1 times the area of each slice, which is pi r squared, but r is going to be the height of the function, so it's x squared. The radius is x squared dx. Ultimately, this gives us pi integral from 0 to 1 of x to the 4th dx. And just remembering our power rule and fundamental theorem of calculus, and the fact that the lower limit is 0, we're going to get that the full area of this object is pi over 5. The next technique we have for integrating volumes is called the washer method. So this combines the disk method and our difference, or the area between two curves, in a kind of way. So basically what we do is we have a solid of revolution, but now we want to have a region that is bounded by one function f of x and the lower function g of x, as opposed to the region between f of x and the x-axis. So when we rotate this around the x-axis, we'll obtain a cone, but with a chunk taken out of the middle. So this will be like a cone that you could put food in or something. Again, we look at a slice. an infinitesimal slice, and we try to figure out, well, what is the infinitesimal volume determined by that infinitesimal slice. So that slice is going to look like what's called an annulus, and since we're thickening it up by dx, we call it a washer. So the idea is that we're going to acquire the volume by adding up all these infinitesimally small washers, or the volumes of all these infinitesimally small washers. Well, of course, the volume of this washer is going to be the area of the annulus times dx again. But the area of this annulus is going to be the area of the cylinder minus the volume of the interior cylinder. So this will be pi r2 squared dx minus the volume of the inside cylinder. So it's r1 squared dx. But again, this represents the height of our function g of x, this r1, and r2 represents the height of function f of x at a particular point. And therefore we get that this volume obeys the formula that is the integral from a to b of pi of f of x squared minus g of x squared, and integrated with respect to dx. As suggested by our introduction, we're going to consider the volume of revolution obtained by spinning the region bounded by x and x squared over the interval 0, 1 around the x-axis. And so we just plug it into our formula after perhaps drawing it. So it's the integral from 0 to 1 pi f of x squared, which will be x squared, minus g of x squared, which is x squared squared, dx. We can extract out pi from the integral, 0 to 1 of x squared minus x to the 4th power. Again, the power rule allows us to say that this is 1/3 x cubed minus 1/5 x to the 5th. Evaluate the limits 0 and 1. The 0 term will cancel out, and we end up with pi times 1/3 minus 1/5. Finding a common denominator, we'll have 15, and that'll give us 5 over 15 and 3 over 15, which will yield 2/15 of pi as a final answer. The next interesting technique we have for figuring out volumes via our integration methods is the shell method. So in general, we'll apply the shell method when we have a function f of x and g of x, where f of x dominates g of x, and instead of rotating it around the x-axis, we rotate it around the y-axis, so we spin it like this. And when we do that for this figure, we'll get this parabolic bowl with a cone cut out of it. When we do this, we see that we can't really use the washer method. Technically we could, because we might be able to replace f of x with a function of y instead. And then we could convert this to our washer method. However, in general, we won't be able to do that for general f of x and g of x. So we need to develop a new technique. So here's how that technique plays out. You're going to get your f of x and g of x. You're going to fix an x. You're going to look at a small chunk of area of width or thickness dx, and you're going to imagine that chunk spinning around the x-axis at the radius x. So this radius of this ring now, or shell, so this is a ring or shell, which is why we call it the shell method. Well, the radius of this shell is x, because that was the x that we chose beforehand. Now, in order to determine the infinitesimal volume of this shell, we need to multiply the circumference times the height of the shell, or the ring, times the thickness of the ring. In symbols, this translates to 2 pi x. That'll exactly be the circumference of this circle that cuts out the ring. The height is just going to be f of x minus g of x, which is actually simpler in some sense than the washer method. And then finally we have to multiply by a thickness dx. Now this is an approximation. The volume, this is depending upon dx, this is not exactly the volume. But in the infinitesimal realm, this is actually the correct expression. And therefore we get that we can obtain the volume of such a body of rotation by integrating from bounds a to b of 2 pi x f of x minus g of x times dx. So let's do our example for the shell method where f of x is equal to x and g of x is equal to x squared. Again, the figure that we're trying to calculate the volume of is this nice parabolic bowl with a cone cut out of the center. And so we can plug it into the formula once we realize that the method required is the shell method. So our bounds are from 0 to 1. The circumference of the shell is 2 pi x. The height of the shell is f of x, which is x, minus g of x, which is x squared, times dx. Of course, we can extract the 2 pi, so we have integral from 0 to 1 of, now the x multiplies everything, so I get x squared minus x cubed dx. And now the antiderivative is 1/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 1. At 0, of course, this collapses to 0. At 1, it's 1/3 minus a 4th, which is ultimately 1/12. And so we will obtain the answer pi over 6.